You get it? Yeah. All right. I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just pray that you just bless our class, help us to understand a little more about chain rule. Again, Lord, we thank you for your sacrifice for us. We thank you that you died on the cross for our sins if we just accept you. We thank you that our righteousness can be your righteousness, Lord, and we thank you for that each and every day, Lord. In your name I pray. Amen. All right. So, let me tell you about this wonderful thing called the chain rule. So what I'm going to do today, guys, I'm going to cover the chain rule and also higher derivatives. And once we've got that settled, hopefully I'll spend about the last half hour of class going over the solution to the test with you guys, okay? So first of all, what's the chain rule? Let me state it for you. The chain rule says the following. It says the derivative with respect to x of g of f of x. All right. So this is the derivative of a composite function, a function of another function. Well, it's equal to g prime of f of x times f prime of x. Let me put this into words. So what I'm writing here is we differentiate the outside function g, right, and evaluate that derivative at the inside function. Which we're calling f. That's the first thing. And then, of course, we multiply that by, this is just the derivative of what? The inside function. Let me just, before I even do an example, let me share with you another notation for this. You could write this. You could say d dx of g of u is equal to dg du times du dx, where u is equal to f of x, to make the connection with the statement above, not in purple. So when I write dg du, that again captures this idea I wrote out in red. It means you differentiate the outside function and you evaluate it at u, where u is the inside function, all right? It's really important that we evaluate the derivative of the outside function at the inside function, okay? That is the heart and soul of the chain rule. Not doing that is wrong. Let me show you examples as opposed to besieging you with more notation here. So how about this? What if I take the derivative? What did I do? Did I do something? No? All right. Derivative of, how about 1 plus 3x squared raised to the 42nd power? Yep.
It's going to be 42
Mm-hmm.
times 1 plus 3x squared times 6.
And that was to the 41st power, right?
First time,
Yeah. Now, this gentleman already knows the chain rule, which is good. Some of you are like, what did he do? What did he do? Right? So for those of you, let me try to unwrap this piece by piece and show you how he knew to do that. So basically the idea here is just to think of this as being u. The inside function we can think of as being u, right? And so what we have is d dx of u to the 42 power. All right. What's the derivative of the 42 power? Well, it's 42 u to the 41, right? But the chain rule says you're not done. That's not it. That's not the answer. Why is it? What's the difference between, can you see the difference between this and this? What's the difference between what I'm underlining in red and what I'm underlining in green? This actually gives me an answer to the question, when do we use the chain rule? How do I know when I need to use the chain rule? There's a simple thing I can tell you. If you're differentiating with respect to a variable, right, and the function you're looking at is not really a function of that variable, that's when you need to use the chain rule. Like, the function is the 42nd power function, right? The variable here is u, but I'm differentiating with respect to x. That means I need to use the chain rule. And so the chain rule simply says, do what you'd usually do in the u variable, but then you have to multiply by du dx. That's the chain rule. Now, over here, I'm differentiating with respect to u, a function of u, right? No need for the chain rule. I mean, what would happen if you were to try to do the chain rule over here? What would it multiply by? Du, right? So it's kind of like, duh, you don't need to do it. I mean, you can always see the chain rule everywhere if you want to, but it's just needless. Okay, so then what is this? So we've got 42, 1 plus 3x squared to the 41 power times d dx of 1 plus 3x squared. But of course that differentiates to 6x, so I got 42 times 1 plus 3x squared times 6x, and then this was to the 41 power. And that, of course, is what the gentleman told us to write down to start with. Because once you understand the chain rule, you don't actually have to write out all that u stuff, right? You can just write down the answer once you really get it. Now, sometimes you'll be asked homework problems which want you to write down the u that you're using to kind of study the substructure of the rule. But that's just a homework problem trying to teach you to learn. Ultimately, what we want is for you to understand how to go from here to there, just like that, right? Shall we do another? Let's do another. What if I have, I want to calculate the derivative with respect to x, so the square root of 1 plus the square root of x. So since we're starting, I'm going to make a starting step. I'm going to call the inside function u, right? So what I have is what? I've got d dx of the square root of u. What's the chain rule say? It says differentiate like usual, 1 over 2 times the square root of u, but then I have to multiply by du dx, right? But what is u here? Here, I'm going to leave this as u to be lazy. What's the derivative of the square root of x again? It's 1 over 2 times the square root of x, right? So this is 1 over 2 times the square root of u, but what was u? U was 1 plus the square root of x. All of this times 1 over 2 times the square root of x. What happened to the 1? Yeah, it differentiates to 0. Yes?
If you, like, I get, I replace the square root with a half.
Uh-huh.
Can I leave it at the end instead of doing the whole 1 over 2 square root of 1? Can I just leave it negative a half?
Yeah. I think you could also write this as 1 over 2 times the square root of 1 plus, I mean, I'm not sure if this is what you wrote, but this might be what you wrote, times 1/2 x to the minus 1/2. That would also be, that would also be a correct answer. Is that what you did?
Yeah.
But you also did that for the big function too?
Yeah.
Yeah, that's also, I mean, indeed. This could also be written as like, okay, so there's a 1/2 and a 1/2. You could write it as 1/4, 1 plus the square root of x to the minus 1/2 times x to the minus 1/2. Indeed, that's another way you could express the answer. Is that what you had?
Yeah.
Yeah, that's fine. Nothing wrong with that. All right. You notice that I've disconnected a little bit from my initial statement of the rule, right? Let me get back to the initial statement. So let's see here. Suppose you have f of x equals to x cubed plus x squared. And suppose you have g of x equals to 1 over x. All right? Let's calculate the derivative with respect to x of g of f of x. So if I follow the chain rule directly, it says I do g prime of f of x, right? Times f prime of x. What does that mean? What is g prime here? X to the minus 1, right? So I get minus 1 x to the minus 2. I get minus 1 over x squared, right? But I think for you guys, that formula, while it's not incorrect, it's just not as useful. Sometimes it's helpful to rewrite this one more step. Think of this as g prime of u is equal to minus 1 over u squared, right? Because if you do that, it's easier to make the next step down here, right? I can say, okay, so g prime, it's really what? G prime of what? Of x cubed plus x squared, right? And I'm supposed to multiply that by f prime of x, which is what? Can we just write that out? What is that? That's, yeah, 3x squared plus 2x. Very good. So in order to calculate this, the derivative of the outside function at the inside function, what do you have to do? Plug in u, basically, this being u, right, into that formula. So that's minus 1 over quantity x cubed plus x squared times 3x squared plus 2x. Or if that's bothering you, you could simplify it, right? This is minus 3x squared minus 2x over x cubed plus x squared squared. Actually, that's not simplified. If I was going to simplify this, what would I do? How would you simplify this expression? Yeah, take out an x. Totally agree with that. So upstairs, you see how to take out an x. You got an x times what? Minus 3x minus 2. Wholeheartedly agree with that. How about downstairs? You can factor out x squared here, right? So you've got x squared times x plus 1. All of that squared, right? I think that's still not as simple as it can be. If I pull x squared outside of the square in the denominator, what happens to it? Yeah, it becomes x to the fourth, right? So this becomes x times minus 3x minus 2 divided by x to the fourth times x plus 1 quantity squared. And now I can finally get to my punchline here. Well, yeah, we can reduce that. Minus 3x minus 2 divided by x cubed times x plus 1 quantity squared. That's a pretty nice formula for the derivative. I'd say that's simple. Simplified. Yeah.
Didn't you take out that 2 right there on the right? The x to the fourth, parentheses, x plus 1, parentheses to the second. Nope. Never mind.
I don't know.
How did you make it x to the fourth then?
Oh, if you have something like, suppose you have like a squared times b, quantity to the, squared, then this is equal to what? This is equal to a squared squared b squared, right?
Yeah.
So that's equal to a to the fourth times b squared. In other words, if I pull a square outside a square, it becomes a fourth. That's what I did down there. Yep.
Are you saying that we have to have it in the final form, like simplified version, instead of leaving it at?
Oh, by now you should know that I wouldn't insist on it unless I insisted on it.
Are you insisting on it?
I mean, sometimes I will ask the question, differentiate, do not simplify. If I ask that question, done right here, right? Game over right here, the differentiation is done. And then that's algebra. But on occasion, I should ask you guys to simplify something because it's healthy for you guys to work on your algebra. And trust me, some of you need to work on your algebra. Shall we do another? Let's make this one more interesting. Let's do something that involves both the chain rule and our old friend, the product rule. You're like, yay! Let's differentiate with respect to x something like x cubed times the square root of 3x minus 7. What did I do? Is it me?
No.
Oh, okay. Just checking. I mean, I as far as I've known, I've at most insulted mathematical concepts today. So, I mean, I could insult something else. Let's see here. What am I writing? The beloved product rule. So you're looking at yourself, you've got fg prime is f prime g plus fg prime, right? That's the pattern, product rule. Now, of course, I don't really need anything too highfalutin to do the first thing. What is this? This is what? Yeah, I got 3x squared, square root of 3x minus 7. Great. And how about the next piece? Plus what? Plus x cubed. And now I got to do the chain rule. Let's see if, can I take off the training wheels? When I say take off the training wheels, can I not write the u? Can you guys follow it? Let's try it. The outside function is the square root function, right? So what's the derivative of the square root function?
Just 1/2.
1/2. 1 over 2 times the square root function, right? But I don't just write square root of x there, right? Because we have to evaluate the inside function. So what do I write there? 3x minus 7. Why do I do that? Chain rule, right? And then times the derivative of the inside function, which is 3, as you told me. So what you're doing here is, the derivative with respect to x of the square root of u is equal to 1 over 2 times the square root of u times du dx and we'd let u equals to 3x minus 7. That was the thought process right there. Now your book, he has the abstract chain rule like I wrote at the start of today, right? And then he also has this power chain rule, or power, he calls it generalized power rule. What's his generalized power rule? Well, I'll get to it in a second here, but let me finish this thought. Oh, that's it. If I say don't simplify, game over, right? That would be it if I didn't bother with simplifying. You guys want me to simplify it?
Why is it times 3?
Chain rule. So the chain rule says I have to multiply by the derivative of the inside function. Inside function here is 3x minus 7. So, yeah. So if I said differentiate, don't simplify, we're done. Right? If I wanted to simplify, I guess what I would do. What's that?
When you just put the 3 on top, or no?
I would make a common denominator of 3x squared times, so making a common denominator gives me 3x minus 7 quantity squared plus 3x cubed. Curses, I got a 2 over here. I'm going to keep it upstairs. I put the 2 up there, see it? And then I should fiddle with this for a second here. So I have 3x squared times 3x minus 7 plus 3 halves x cubed, all divided by the square root of 3x minus 7. See, can I simplify that? Maybe a little bit. That gives me 9x cubed. What's 9 plus 3 halves? Indeed, 21 over 2 x cubed minus 21x squared, all divided by the square root of 3x minus 7. In my book, that's simplified. You could factor out a 21, I suppose. And an x, okay, fine, you got me. All right. You've driven me to it. 21x squared times 1/2 x minus 1 divided by the square root of 3x minus 7. Now, in my book, when I say expression is simplified, it's not just a vanity of convention. When I say this expression being simplified, I want it to be in some kind of format which would allow me easy analysis as I go on. The reason I like the things that I've underlined here in green as being simplified is it's pretty easy for me to tell you where these expressions are not defined and where they have zeros. I can easily look at this one here. I can tell you this is not defined at 0, and it's not defined at -1. Yeah, vertical asymptotes in the graph of this thing. And then where is this 0? It's going to be 0 at 2/3, right? Because I could just set the denominator, the numerator equal to 0, and then I can see that it's got a 0 at 2/3. Minus 2/3, sorry, right? Minus 2/3. And likewise over here, you can see that there's zeros at 0 and 2. And then downstairs, it's not going to be defined when this is 0, which would be like, what, 7/3? So that's the advantage of the simplified expression. It's much harder for me to look at the thing which we got to right after we were done differentiating, right here. Like if I asked you, where's that 0 and where is it undefined? Undefined, I think we would all get, right? That's where the square root's 0. That's fine. But the zeros, they're kind of hidden in this expression, right? Whereas they're just sitting out for us to look at in this expression. That's why it's worth simplifying if you want to do further analysis. Yep.
When you squared the square root of 3x minus 7, where did you get the square?
Oh, I made a common denominator. So what I did in the step above is I just looked and I searched my heart and I saw that there was a 3x minus 7 divided by a square root of 3x minus 7 there. It just hadn't been written yet. You see? And then when I did that, I was able to add these fractions together because then they had the same denominator. So this came from making a common denominator with this. That's where it's from. See, the calculus does not bother you guys. All of your questions are about algebra. Am I right? Yeah. It's almost like you were cheated, like you never had a proper course in algebra. Curious. Okay, here, let's look at another example. How about ddx of, x squared over the square root of x cubed plus 1 over x? How do you want to do this one? There are two ways to do this. Two obvious ways. Product rule or quotient rule? Which one do you want me to do? You want to do the quotient rule? Oh, fine. You guys are gluttons for punishment. So that would be 2x times the derivative with respect to x of the square root of x cubed plus 1 over x minus x squared. Oh, I'm an idiot. That was on the next one. Sorry. Remember the product rule. It's quotient rule. F over g prime is f prime g minus f g prime over g squared. The minus goes on the derivative of the denominator. So I have 2x, which is my f prime. G just sits there, minding its own business, x cubed plus 1 over x. Then I subtract xf, which is x squared, times the derivative of g, which I'll write symbolically here because I don't want to do the chain rule and the quotient rule all at once. So I'm writing it as unfinished business right there. And then downstairs you got square root of x cubed plus 1 over x, quantity squared. That's just quotient rule, right? Not done yet, right? What do I have to do? This one, right? Yeah, chain rule. So what's that derivative? Oh, all this mess. Ugh. So I do 1 over 2 times the square root of that junk, otherwise known as x cubed plus 1 over x, times the derivative of that, which I'll put in the parentheses here. Okay, 3x squared. Minus what? Minus 1 over x squared, yeah. And there you go. That would be it, if I didn't say to simplify. Yes, sir?
I should definitely know this by now, but the derivative of any square root, is the derivative of anything like square root is just 1 over 2 square root or whatever that is?
Indeed, the derivative with respect to u of the square root of u is 1 over 2. So now that we're doing the chain rule, I find it instructive to write out these. I don't know, it's a psychological problem I have. But for me, it's helpful to rewrite the rules of differentiation.